surface area. So just as with arc length, there's sort of like a nice little build-up explanation to what surface area is. And we're talking about specifically surface area from a solid of revolution. The punchline of all this explanation is that there's going to be a formula for a surface area. So I'm going to very quickly go through the explanation, and then I'm just going to show you the formula. And as far as doing problems, naturally, I know that's what you're going to use. So, surface area. First of all, how do we approximate it? Well, with the solid of revolution, the easiest thing we could possibly have is a straight horizontal line. If you take a straight horizontal line and rotate it around the x-axis, what kind of shape do you get? You get a cylinder. We know the surface area of a cylinder. We talked about that when we talked about shells. So the surface area of a cylinder is just the circumference, 2 pi r, times the length h, which we're now going to call L. So 2 pi r L. Okay. But what if the straight line isn't horizontal? What if it's at an angle? Yeah. So you can work it out, but I'll just give you, again, it's going to be a series of punchlines. The punchline is what you wind up with is something like a shape that I have a picture of over here. This thing is called a frustum. What? A frustum. Yeah. That's just what it's called. Okay. So what is the surface area of a frustum? Again, I'm going to skip some of the details and I'll give you the punchline. The surface area is, well, once again, it's 2 pi r L, but with a small difference. The L we interpret as the actual length of the line. We don't think of the height of the thing. It's actually the length of the line itself. So keep that in mind, first of all. Second of all, R, now obviously there's not a single radius. So what does R, the radius, represent? R is the average radius. Now that's not going to bother us so much because in a second, what's going to happen to this frustum when we take tiny dx's?
R is going to be just an R.
The frustum is going to become very, very thin, and the average radius, you're taking the average between one radius and another radius that are very, very, very similar. So the average radius just becomes the radius of the frustum. And then also, L is just saying, what's the length of that line? Well, do we know how to find the length of a line? I sure hope so. We just spent a whole hour working on it. Okay. So, to approximate the surface area, what you have is the sum of the surface area of each frustum. So the surface area of one frustum is 2 pi r times L. But what was L? We know an approximation for L is the square root of 1 plus delta y over delta x squared times delta x. We just saw that. So if we want the surface area exactly, what happens? The integral of 2 pi r times the square root of 1 plus dy dx squared all dx. And what is R? Well, we've had to think about previously what R is when we did the volume of a solid of revolution. So for example, when you rotate around the x-axis, R is just the y value. And when you rotate around the y-axis, R is just the x value, how far you are from the y-axis. And if you don't believe me, once again, draw the picture. So a quick note. When we had solids of revolution, and we talked about this before, choosing dx or dy, rotating around the x-axis or y-axis, in one case we had disks, and in the other case we had shells. Here, we do not have that problem. And we discussed this before. Why don't we have that problem? Because when you take a line and you rotate around the x-axis or you rotate around the y-axis, what shape do you get? You get the exact same shape. You either get a frustum around the x-axis or you get a frustum around the y-axis. So it's the exact same shape, therefore it's the exact same formula. So we don't have the disks versus shells problem when we're doing arc length and then surface area. Okay. So find the surface area when, it's a very simple graph, function y equals x is rotated around the x-axis. So I'm going to abbreviate surface area as SA because I'm very clever. All right. So what is the surface area? How do we set this up?
Okay, fine. So, it would be integral of 2 pi. The radius is going to be dx and times 1 plus.
Okay. So first I'm just going to write the general formula. And now I'm going to sketch the picture to help us think about
From 0 to 4.
what happens. Well, when we take a little dx and we rotate it around, what kind of shape do we get? Well, we get a slice of a cone, which we're calling a frustum. So if you want to call it a slice of a cone, that's okay too. Okay. But yes, the entire shape itself is a cone. And one little slice gives you a frustum. Now, what is the radius on that? Yeah, the radius is just the function. But what's the function? Function is just x. And what's y prime?
1.
Y prime is just 1. So you square it. So this is actually going to work out in pretty simple fashion. So you get this. So, oh, and there's one thing missing. Sorry.
0 to 4.
The boundaries. We know we're going from 0 to 4. So I pull out the 2 pi because it makes my life simpler. From 0 to 4, x times radical 2. Oh, okay, yes. We can even just pull out the radical 2, and now we're just integrating x. What's the integral of x? X squared over 2. And this goes from 0 to 4. So we get 2 pi radical 2. Plug in 4. 4 squared over 2 minus you plug in 0. You'll get 0. So this is just, so that's going to be 16 over 2, so it's 8. So you get 16 pi radical 2. So we actually found the surface area of this cone. What about when we rotate around the y-axis? Y equals x squared, but I'm going to rotate around the y-axis. Well, you know what? get a frustum, but around the y-axis, and you set it up exactly the same. You can still do dx. So the surface area equals the integral from 1 to 3 2 pi r square root of 1 plus y prime squared dx. Now, what's the radius in this case? Well, let's find it on the picture. The radius is from here to here. And that length is measured by what? That's x. So the radius is just x. And y prime, of course, is just 2x. So there's the setup, and I'll say that it's a doable integral, and I'll fill in the details later. Okay. So to finish up this problem, we have the integral from 1 to 3, 2 pi x, then inside you have 1 plus 4x squared dx. We can actually see things a little more clearly if we put the 2 pi on the outside. So, how do you do this integral? Well, we've got a square root and some things under it, and that actually suggests we've got an inside function, so we should think about doing a substitution. So let's see if that works. U equals 1 plus 4x squared. Du equals 8x dx. So is that close? Well, what do we want to replace? We actually want to replace x dx. So we're almost there. We just want 1/8 du equals x dx, and we're on our way. So this equals 2 pi, the integral. And we're going to have square root of u, so u to the half, and then du, and I'm going to take that 1/8 and I'm going to put it out front. Okay. So now we've got, simplify out front, we've got pi over 4. All right. Now u to the half, integrate, you get u to the 3/2, and 2/3 of that. And we've got to go back, replace that, so u was 1 plus 4x squared to the 3/2, and x goes from 1 to 3. And now you evaluate and do the arithmetic. So you get 2/3, 1 plus 4 times 3 squared to the 3/2. Minus 2/3, 1 plus 4 times 1 squared to the 3/2. And so that gives you, okay, so 2/3 times 37 to the 3/2 minus 2/3 times 5 to the 3/2. And to be sure that doesn't work out very nicely, so you can leave it like that, or you can get in a decimal approximation.